Hello, everybody. Welcome to today's webinar. I'm just going to give a quick minute here for everyone to get in, and then we will kick things off. So just a quick minute, as there are people still joining, and we don't want to jump ahead too quickly here. Okay, I'm going to start. So hello, everyone. I'm Renee Yager. I'm the Director of Marketing here at EPC, and welcome to today's webinar, GaN-based solutions for cost-effective direct and indirect time-of-flight LiDAR transmitters. Before we get started, I will just go over a few housekeeping items for today's event. You will have the opportunity to submit text questions to our panel by typing those questions into the Q&A feature at the bottom of your screen. You can send those questions in at any time. We will collect them and address them during the Q&A session at the end of today's presentation. At the conclusion of the webinar, we will be selecting one participant at random to receive a copy of the 3rd edition textbook, GaN Transistors for Efficient Power Conversion. If you are the lucky winner, we will contact you in the next few days for your shipping information. Now, let me introduce our panel and speakers. On the panel today is John Glazier, PhD. John is EPC's Director of Applications, where he develops applications, circuits, and methods to maximize the benefits of GaN and to help engineers realize the advantages of GaN technology in their designs. He is our resident time-of-flight LiDAR expert, having designed all of the LiDAR demo circuits that we have available today. He has published more than 35 papers and has been granted 33 US patents and 12 non-US patents, with several more pending, and is an IEEE senior member. Thanks for joining us today, John.
Thanks.
Now I'd like to introduce our speaker today. Alex Lido is the CEO and co-founder of Efficient Power Conversion. As a co-inventor of the HEXFET Power MOSFET, Alex holds many patents in power technology, semiconductor technology, and has authored numerous publications on related subjects, including co-authoring the first textbook on GaN transistors for Efficient Power Conversion. Alex, thank you for joining us today.
Thank you, Renee. And I should say that I co-authored that one with John. So
that's right.
You got all the book writers here on the call. So anyway, today we're going to first introduce, the audience to LiDAR and laser diode drivers. LiDAR stands for light detection and ranging, and it's becoming extraordinarily popular in a whole variety of things. Most famous, of course, are autonomous vehicles. And then we'll talk a little bit about why gallium nitride. It's really an enabling technology, and just about every LiDAR system that you see out there will use gallium nitride, primarily from EPC, in order to fire the lasers. And then we'll talk about picohenries, strange little subject, but do they really matter? And I'll explain why they do matter and really need to be focused on. Finally, we'll get into the state of the art, and this is a very timely webinar. We just introduced a new time-of-flight IC that's very exciting. We'll talk about that, and we'll also talk about the future, where this technology is going in the near term and what to expect. So first of all, what is LiDAR? This is a very simplified block diagram. Again, it stands for light detection and ranging. And there's a laser transmitter that shoots a beam of light. This is a scanning LiDAR system. There are many types. We'll talk about a few different types. And that beam is then transmitted out from that scanning, spinning mirror or MEMS mirror, or various ways of creating scanning optics, and it reflects off a target. That reflected beam goes to a receiver. And depending on how long that light was hanging out there, it tells you how far away those objects were, and you can get a point cloud such as you see in the lower right-hand corner. Now, there are many types of LiDAR systems. There's time of flight. We sometimes call it ToF, that is very good for distance measurement. There's also Doppler effect and spectroscopic, multispectral, polarized. Sometimes you hear these, a couple of these characterized as frequency modulated continuous wave. That would be a time of flight and Doppler system in combination. But today we're going to talk about time of flight distance measurements. It's perhaps the simplest of all of these methods, and at this point in time, it's by far the most common in all the new systems that you're seeing come out there. And speaking of which, this is just a very abbreviated list of some of the applications that products, lidar products, are being used in today. If you look on the lower right, it's the most famous one, autonomous vehicle navigation. Most of the lidar systems that you hear about are associated with autonomous cars, and hopefully someday we'll see full autonomy in these vehicles. Now I'm also indicating here LR for long range lidar and SR for short range lidar. And I've indicated in all these applications where it needs long range and it needs short range, sometimes both. And we'll talk about that because the methodologies are different if you want to see something close in versus far away. An example of a short range lidar system would be, up there in the upper left-hand corner, one in a lidar robotic vacuum. That sounds exotic, but these are actually consumer robotic vacuums that you can buy that use very simplified lidar systems to both map the room and do collision avoidance. Speaking of which, in the lower left-hand corner is a drone, and drones use lidar both for collision avoidance, and consumer drones have lidar systems now for collision avoidance, but also they mount lidar units, like in the picture here, long-range lidar units for mapping, for example, architectural sites, discovering new architectural sites, or doing inspection of power lines remotely, or offshore windmill maintenance and detection systems. So that's another one where you have both kinds. And so you can see there's just a variety, and just about anything that moves, any time that you want to have an understanding of your surroundings, for example, like an augmented reality where you need to have a virtual reality mixed with a real reality. Those are all examples where lidar is becoming the most common way of creating that awareness, and also the most cost effective. And as we get the cost down, you will see it in everything. So let's talk about the types of time of flight lidar. And there are two common types, DToF, which stands for direct time of flight, and IToF, which stands for indirect time of flight. Now, direct time of flight is perhaps the simplest to understand. You just fire a beam of light, a packet of photons, and it bounces off an object and it comes back at a later time. And the measuring that time difference tells you how far away that object is. Now, if you're real close in, that's hard to do because the time difference is very, very slight. So another methodology called indirect time of flight measures actually the phase difference between a pulse train that goes out and its reflection. So the difference in phase really can tell you how far away an object is. And these are sometimes called flash lidar, and you can, we'll talk a little bit more about it, but they can be very, very low cost and are becoming popular very quickly. So let's look at direct time of flight and what's important there, and why pulse shaping is key. This is an example where you're firing a packet of light and it has a pulse width of t sub p in this case, and it reflects off of two objects. So you get two pulses back, and each of those pulses can be measured independently to tell you how far something is away. And the distance is just the speed of light times the time delay divided by 2, because the light has to do a round trip. And the difference between these two pulses tells you the distance between those two independent objects, which can be important, obviously. Now, If you have a longer pulse width, as in this image, it becomes harder to distinguish between two objects. So, and of course, how do you know which one is which if you just get one long pulse back? And in fact, the resolution can be very simply expressed this way, that for every nanosecond, you get about 15 centimeters of resolution. So if you want to see objects that are a meter apart, you better have a pulse width that's less than 6 nanoseconds in width. On top of that, you have to add other imprecisions in the system, but that's a good gauge of the way to tell what resolution you need. So it's clear that the shorter the pulse in direct time of flight, the better your resolution. Now, in indirect time of flight, where you're measuring objects that are close in, you have a pulse train, and this pulse train tends to be a burst of, hopefully close to square wave pulses of light. And when they come back, you subtract the incoming from the outgoing, and you get a pulse that's equal to the phase difference, which is proportional to the distance. However, if that pulse train is not very square, you get, for example, in the lower part of this image there, let's say triangles, it's much harder to tell what the phase difference is. If there's any rounding in it or whatever, it becomes equivalent to a blurry image, and it requires a lot of extra computation to try to extract a better understanding of an object close in. Now, what about amplitude? Amplitude is important because basically the higher the amplitude of the pulse, the farther you can see. The amplitude is, how much power you can put into a laser in a pulse, and that's equal to how many photons come out. But there are limits, and these pulse energy limits come from two things. One is you run the laser with a very high current pulse repetitively, and it's going to hit its thermal limit. And secondly, and probably even more important, there's an eye safety limit. If you're firing these lasers, just think about a whole freeway full of cars firing these lasers everywhere. There are eye safety limits. You don't want to be blinding people with your lidar systems. Now, one thing is true, though, is if you have a narrower pulse, you can have a higher amplitude with the same energy. So narrower pulses afford a higher amplitude, and therefore you can actually conceivably see farther. You can see better without hitting thermal limits in the laser, and you are farther away from eye safety limits. Let's talk a little bit about the photon generators, the lasers. There's been an enormous amount of progress in laser diodes, driven a lot by the need for lidar systems. So in the upper right-hand side, I'm showing an OSRAM surface or side emitting laser. That's in a package. The package is of course clear. In this case, there are 4 of them mounted in parallel. And you can see the little schematic in the middle of the page on the upper side, where light is actually emitted out of the side of the laser, and it's extremely efficient to do it that way. So these are the most efficient types of lasers. Now, at the bottom, we have the what's called a VCSEL, which is a vertical cavity surface emitting laser. And vertical cavity surface emitting lasers are relatively new. They are much less efficient, but as you can see, that array on the lower right, that's got hundreds of these little VCSELs. So each one of those can be made. They're made all at the same time, just like a semiconductor, and each one of them conceivably can be fired differently than the other ones to create all sorts of interesting patterns of light. All of these need to have a very fast response. Definitely you have to be able to fire these lasers in less than 100 picoseconds. And you need conceivably a lot of power depending on how far you want to see. If it's close in, a watt's okay. If it's farther away, you might need a kilowatt or even more. And of course, they need to be cost effective. All of these are available in a bunch of different wavelengths, from 850 nanometers up to 1550, with the most popular being the 905 nanometer for a lot of reasons. It's the lowest cost kind of laser. It's also extremely efficient. But the 1550 nanometer is getting a lot of attention because it has higher eye safety limits, but it is a much more expensive and less efficient type of a laser. So those are the two systems that we see out there today in the majority of cases. So let's talk a little bit about direct time of flight and the practical requirements for the electronics involved in direct time of flight. So here you have a rather bizarre car, and it's trying to see an object 200 to 300 meters away. As we saw earlier, you have to have a narrow pulse. As a matter of fact, if you want to see things at that distance with reasonable resolution, you need pulses between 5 and at the worst case 50 nanoseconds. 50 nanoseconds, of course, would only be able to resolve something that's about, I guess, about 7 or 8 meters apart. So really, you want to be closer to 5 nanoseconds, but you need a lot of power in that laser, between 50 amps and 500 amps, depending upon the efficiency of your lasers and the efficiency of your optical detection, and also the optics, how well you can maintain a collimated beam going out that far. Now, for short in, if you're using direct time of flight, and that's John's dog, let's see, Luna, who is obviously not very aware of the car coming up. But so you want to be able to detect things pretty close in, up to 10 meters, 0 to 10 meters. And that means you need really short pulses, half a nanosecond to 5 nanoseconds, or even less if it's closer in. And you can do that with lower power. About 10 meters takes usually about 10 amperes to see that far using direct time of flight. But again, it becomes tricky because you need very narrow pulses to see precisely the objects close in. So when you get close in, you tend to go to indirect time of flight, as we mentioned earlier. Now, IToF uses a non-collimated beam. It's like a flashlight and like a flash bulb, actually, better. And therefore, it takes a whole lot more energy to get enough photons to see a faraway reflection. I mean, you've all had that experience where you're trying to take a flash photo of the moon, right? It doesn't really work very well. And so if you're looking at targets up to 10 meters, well, then the light doesn't disperse very much. So it's lower power, maybe up to 10 amps. And your pulses need to be pretty quick, so that you can see this phase relationship of a short in subject. So you're really looking at 50 to 200 megahertz, which modern systems tend to be leaning in the 100 to 200 megahertz range for these pulse trains. They're bursts of pulses. For long distances, you can get lower frequencies, but again, your power goes up at a very rapid pace. It's not very good for very long distances. So let's look at the basic laser drive circuit. And it's very simple. It's deceptively simple. You have a bus capacitor, C bus. It's charged up by some sort of a voltage source. And then you have a laser, DL, and you have a GaN device. I'll explain why it's GaN, Q1. And when you turn on Q1, as you see there, then you can discharge the bus capacitor through the laser and it emits light. Very simple. When the bus capacitor is depleted, the current goes away and you can take away the signal. So in this case, and this is called a resonant circuit, all you've had to do is very quickly discharge the bus capacitor through the laser and you get a very short pulse. So why is GaN being used in all this? And there's a very simple reason. It started way back when Google mapping was going on. They wanted to use digital mapping the three dimensions around it. And so it spawned this development of a lidar system that had high enough resolution to do mapping of streets and things like that. That evolved into autonomous vehicles that you know about today. But the reason GaN was used even in those very early systems is because it's so blazing fast. So here's a comparison. The alternate technology is a silicon MOSFET. And here we'll take two devices, and it's best-in-class silicon MOSFET against a modern eGaN FET. We picked 100 volts. I'll explain why voltage is important. Sometimes you can do lower voltages. Sometimes you need higher voltages, but 100 volts is the most common voltage used today. You can see that the on resistance of the eGaN FET's a little lower, but the pulse current capability is about the same. So these are comparable devices, comparable as you can get between two very different technologies. Now, the speed of a device turning on and off is somewhat limited by how fast you can charge or discharge the gate of that device. And that's related to the gate charge and the resistance internal to the device and the gate. So here's a comparison. I've outlined it in red, and you can see that if you use as a figure of merit the gate resistance times the gate charge, there's about a 5x difference. And so that means that practically speaking, your FET is going to turn on 5 times faster if this is all that you're doing, is charging and discharging the gate. However, there is more. And we will explain in a little bit more detail that one of the biggest limitations is actually the inductance in the circuit. And so remember, because you'll need this information later, look at the comparison of the inductances. And that's by virtue of the fact silicon MOSFET is a much bigger chip, but it's also in a package. And it needs to be in a package because it's a vertical device rather than a lateral device. And so you have gate inductance of 3 nanohenries, a source and drain inductance together of 1.3 nanohenries, compared to 30x less in the eGaN FET. We've also highlighted the fact that the device is much smaller in GaN, and that means you can cuddle right up to the laser and eliminate any PC board inductances that are there as well. Added benefit, of course, is that you can get these things in automotive certified AEC Q101, but the best-in-class MOSFETs are not available in that at this point. So let's see why that inductance is so important. So we showed you this circuit, and it's pretty simple. However, it's really not so simple because when you look at all the parasitic elements, they are really the thing that limits the performance. And I've circled here in the lower portion 3 key inductances that 2 of them are the common source inductance. That would be between the driver and the FET, and then the between the FET and the return to the gate driver. And then there is an inductor below that, and that's part of a power loop inductance. The one above it is part of the power loop, and then the one above the diode is also part of the power loop. So you have power loop inductance, and you have common source inductance shown here. Let's first look at the impact of power loop inductance. And remember back there at that benchmarking how much higher the inductance in the drain and source were in the MOSFET. And here we're going to try to squeeze 40 amperes out of a circuit in 3 nanoseconds. So this would be discharging a capacitor in 3 nanoseconds, and you got to do that through an inductor. And what's the required input voltage? It's very key, very simple equation, LDI/dt. And let's use 5 nanohenries as just a way to look at this, and you can see that you need 150 volts in order to squeeze 40 amperes in 3 nanoseconds through 5 nanohenries. So in this case, inductance truly limits the performance. So the inductance really starts with the transistor. I showed you that benchmarking against the MOSFETs. These are 3 of the most popular transistors, GaN devices that are used in lidar systems today. The one on the right, it's a 200 volt device that can do more than 200 amperes in pulses. and is popular for the long range, like you need for ADAS5 kinds of systems. The one on the far left is a smaller one. It's probably the highest volume one, and it's good for medium ranges, 100, 200 meter range multi-channel systems. And the one in the middle is just in the middle, as you can see, and it's also very popular in lidar. All of them, because they're chip scale, have virtually zero inductance related to the device itself. So let's look at practical power loop inductance. And I'm going to, again, try to squeeze that 40 amperes out in 3 nanoseconds. And let's see what required input voltage we need. First of all, the power loop includes the main power FET. So that's the eGaN FET, the capacitor bank, all the mounting area for the laser diode. And also, if you have need for current measurement, there's a current measurement shunt in some cases. If you take out the laser from that equation, this is the range of power loop inductance if you use an eGaN FET. Remember, if you were using a MOSFET, it would be all the way over the right, somewhere north of 1 nanohenry just from the FET itself. You add the capacitor bank and stuff like that, it would be in the 2 to 3 nanohenry range. If you include the surface mount laser, even the best of them, you tend to get in this range. So now you're in the 1 to 2 nanohenry range. If you use a through-hole laser, you are off the charts. So we're not going to go there. So this is really the range that you have to work with. Better surface mount lasers are more to the left. The more common ones and lower cost ones are off to the right. So let's look at another part of the inductance system, and that is the common source inductance. And the question that we want to ask is, does 50 picohenries matter? Now, for those of you who work in circuits all day long, 50 picohenries is not very much. But yes, if it's there where we've circled it, common source inductance, it really matters. And let me show you how. So in one of these LiDAR circuits, you have DIDTs that are on the range of 100 amps per nanosecond. These are rates of change that have never been experienced in the world of power before and have only been enabled because of GaN. We see things even as high as 200 amps per nanosecond. But let's use 100 amps because the math is simpler, and let's put in 50 picohenries, and LDIDT comes out with 5 volts. Well, 5 volts is all it takes to turn on and off the GaN device. So you basically are fighting the voltage, the 5 volts you're trying to put on the gate, you're fighting with the inductance, with the voltage generated across that little tiny 50 picohenry inductor. So 50 picohenries matters a lot. I would say that 50 picohenries is out of the park. You cannot do that. You have to have better than that. So you're really, it is so important to have these tiny chip scale devices that can cuddle right up to your lasers, but also have very little internal inductance that might add to this common source inductance. So let's look at the state of the art. And if you remember, I showed you a 200 volt device among the popular chips that are being used. We're going to look at this device. This is through a demo board that you can buy from EPC. And the peak on this thing is 221 amperes. That's the yellow hump there. 221 amperes is being pumped through this device. The bus voltage is 150 volts. And it's going through there in less than 3 nanoseconds. So, as we said, that was kind of a benchmark performance. You want to see about 3 nanoseconds. Gives you about 45 centimeter resolution, even at 300 meters. And the optical pulse is shown in blue, so that the receiver is seeing it in under 3 nanoseconds. So that's pretty much the state of the art today, and it's very useful for long range autonomous vehicles that have to see things clearly to hit the brakes if they need to. So we showed that common source inductance is a very important thing, and it really comes from that circuit that's outside the FET that goes through the driver IC, which is typically made in silicon and goes back to the FET. And it has a noticeable effect on performance. Even 10 to 20 nanoseconds is a couple of volts, and that will slow down your device at 100 amps per nanosecond. So EPC, just yesterday, as a matter of fact, launched the 21601 laser driver IC, which includes the driver and the output transistor all on one chip. It's a 40 volt, 10 amp FET, and it has all the integrated gate driver that's good for 2.5 up to 5 volt logic level input, and it's teeny tiny, 1 millimeter by 1.5 millimeter, which is smaller than either the FET or the driver in prior generation systems. So with this integration, we've been able to get the common source inductance down to a single digit picohenries. I mean, really nothing. And so you no longer have that as a performance bottleneck. You replace several parts with a single part, which is always good. It's good for reliability. It's good for assembly costs, and also reduces your area. This is selling for less than $1 in large quantities, like 500,000 units. So this is a very good way to get into low-cost consumer type applications like tablets and phones, and robots, consumer robots and things like that. Let's see what it'll do. This is a oscillogram showing you the 10 amp pulse on a 20 volt bus, which is pretty hard to achieve. And it's a 9 nanosecond wide pulse. But look at that on time, 400 picoseconds, off time, 320 picoseconds. So these things are pretty darn fast. Now let's look at it doing a pulse train. In this case, we're putting out a 1.4 nanosecond wide pulse. Rise time is against 20 volts and 10 amps, and it's a 5 nanosecond repeat, which means we're running this at 200 megahertz, which is kind of at the high end of the modern IToF systems. So all of these things, are you can buy off the shelf from EPC. These little development kits, like the 9150, which is for that 200 ampere pulse. That oscillogram was measured right off of this demo board. There's an intermediate range, and then there's the brand new one that comes with this IToF driver, the 9154, which again, those oscillograms were measured right off of this board, and it has a little interposer there to the right of the white circle. The circle is circling the IC, and that interposer allows users to put any kind of a laser diode on there with very, very low inductance between that and the FET, so that you can test various different configurations of lasers. And of course, schematics, Gerbers, everything is available on the EPC website. This is the beginning of a family of parts. Coming up in a couple of weeks is the LVDS, or low voltage differential signal input version of that same chip. It's the same form factor, has the same voltage and current capability, and you'll get that March 16th. So that's a very useful for certain people who have noise issues and things like that they have to worry about. Now, one thing that we realized at EPC when we were getting into this LiDAR business is that GaN devices in LiDAR are being asked to do something that has never been asked of a power device ever before, and that is, let's have DVDTs of 300 volts per nanosecond. Let's have DIDTs of 200 amps per nanosecond, and let's do that forever. So we needed to develop our own reliability testing to make sure that didn't generate some new intrinsic failure mechanisms that had never been seen before, since these kinds of requirements were never there before. So we created a test that's been ongoing now for more than a year. and we put in this case a 60 ampere pulse into our medium-sized devices with 1.6 nanosecond wide pulse, and we do that repetitively over and over and over again. Here you see pulse performance. Again, peak current is 60 amperes, pulse width is 1.6, and that's taking it out to 13 trillion pulses. An estimate of the maximum lifetime of an autonomous vehicle is about 4 trillion pulses. There's now 3x. It continues. All of the FET parameters are totally stable after 13 trillion cycles. So at least so far, again, this is with 2 different types of automotive certified parts. And so far, we have seen no new failure mechanisms from this extraordinary speed of these devices. And by the way, there is a very thorough description of not just this test, but all of the intrinsic failure mechanisms of eGaN devices on our website in our phase 12 reliability report, where we give the basic physics behind all the intrinsic failure mechanisms in GaN devices and ways to predict lifetime given an arbitrary set of requirements or missions in applications. So just to bring it home here, time of flight LiDAR drivers are a pulse power application. These pulse requirements differ with the LiDAR range and, of course, their purpose. When using GaN FETs, it's inductance that determines the ultimate performance. If you're using a silicon device, it's the silicon that determines the performance. And of course, eGaN FETs are the best choice for high performance laser drivers. And I hope we've convinced you of that in many dimensions here today. All right, Renee, back to you.
All right, well, thank you very much, Alex. So now we're going to start answering the questions that have been submitted during the presentation. And just as a reminder, you can still submit questions through the Q&A feature at the bottom of your screen. So feel free to do that as we move along here. Okay, Alex, so the first question is, you had mentioned wind turbines as an application for this type of LiDAR. Can you repeat what was that, the details of that application?
Yeah, so there are actually drones that are being used today to fly out to offshore wind turbines and do detailed inspections to make sure that that everything is working. There's no corrosion, and the turbines are turning and things like that. And that is a whole lot cheaper than sending people out on a boat to do that. So it's a pretty popular application for some high-end drones today.
Okay. The next question is, have these devices been used or tried in aviation applications?
Yes, there are lots of aviation applications. Actually, they've also been tried in space applications. Docking with the International Space Station is done with our eGaN FETs and a LiDAR system. But in aviation, I'll take it in 2 dimensions. One is they fly LiDAR systems on airplanes to do ground surveys, to look for example, a tree coverage, or even looking at whether or not there's damage to forests from wildfires and things like that. They also do it for architectural surveys. Archaeological surveys. With LiDAR, you can resolve such fine differences in the ground, the elevations of the ground, that you can actually see patterns emerge from ancient cities, and it's pretty exciting to see that. The other area where it's being explored but not yet deployed is in avionics. Is LiDAR a useful tool to enhance aircraft safety, much like autonomous vehicles and the safety there that can come from that? So we'll see. The good news about LiDAR is it's extremely straightforward. It doesn't require an awful lot of signal processing if you're doing a direct time of flight measurement. So that simplicity breeds accuracy and also a reduced latency when you try to understand your image and run it through like a graphic processing unit.
Okay. What is the best option or choice to select the C-bus bus capacitance?
Boy, I'm going to turn that one to John. What you got?
All right, so I'll give you the best answer I can give. In the high power applications, it's typically resonant because you have so much current that the laser has stray inductance. There's still some on the printed circuit board, and so you have to estimate that inductance. You saw is in the range of maybe half a nanohenry to maybe 1 to possibly 2 nanohenries. And then you can calculate the capacitance you need to get the pulse width. So that would be for a resonant system. For time of flight, where you're trying to get a square wave, then you just use a large capacitor because you're trying to not discharge the capacitance during each pulse. It's more there just to hold the bus up. We have an application note that also covers a lot of that. I think it's ANO27 or something like that.
And these are all ceramic caps, right?
Yes, they're all ceramic. For resonant system, you usually use like NPO. Ceramic seems to work fine, and they also got tested in the reliability test study just because we had to put them in there. For the rectangular pulses, you'll use a combination of maybe NPO and then some high dielectric like X7R.
Okay.
All right, thanks.
Next question is, what is an accurate method to sense the current making it to the laser?
Oh boy, that's a good John question. And John, talk about some of the tricks you've used there.
Okay, so our high power demo boards, we actually use a shunt, and the shunt is a lot of resistors in parallel, basically 5 or 6 typically, and they're small, 04, 02. And they work because in the high power systems, the laser duty cycle is limited because of the laser, and it's typically 0.1%, maybe 1%. And so the resistors can handle that for those very short pulses. In addition, we actually do some frequency compensation on the resistors because of the resistors have a shunt inductance, and that's we think it's pretty accurate. We've worked with some companies that make lasers who've done optical measurements to correlate with what we have, and we're within 10% or so of what their measurements are, and we're continuing to kind of hone in on that because nobody else is measuring this stuff, so we kind of had to figure out what we needed to do on our own. In the future, we'll probably be looking at some magnetic current sensing, that might be in some ways a little simpler, and you don't have to deal with the added inductance of the shunts and the rest. But that's a little bit down the road.
But that's definitely a very tricky part of this whole game.
It is, and we get asked that question, and there's going to be continuing work on that.
Are there any improvements envisioned in getting the heat out of these smaller chips?
So first of all, the FET itself tends never to be the thermally the hottest component on this board or in this system. It's the laser. Lasers are the most expensive component, and they tend to be run at their limits. So we really haven't had a lot of thermal issues at all with even the teeny tiniest of our devices running at full bore. Now those things may change over time. I think with IToF, there's a little bit more burden on the device compared to the laser, but it's still nowhere near the thermal limits of the FET.
Are you seeing many military applications?
Yes, the commercial devices are sold to lots and lots of military contractors. There's all sorts of very interesting systems that allow for soldiers on the ground to be able to see with their point of view based on lidar input or lidar three-dimensional images that are generated by drones flying above them, because that's a simple image processing thing. So there's a lot of work being done there, and some of it very exciting and pretty cool to see.
What maximum repetition rates can be expected for eGaN FETs used in DToF at currents greater than 100 amps?
John, what do you think?
I think that's, it doesn't appear to be limited by the FET. There's two things. One is it's how hot the laser gets, which has a lot to do with, the relative duty cycle of the laser. The high numbers I've been seeing for most people are around, 1%, and that's where they do a lot of, they put a lot of effort into thermal management of the laser. And I've seen people go up to maybe a megahertz in those applications. So for IToF and the high current, that's kind of at the edge of what we see. Most people are well below a megahertz.
Yeah, you're saying DToF, for DToF, right?
For DToF, yes.
Yeah. For
Yeah,
IToF
for DToF.
at 200 megahertz, what's the repetition rate of those bursts?
It depends. It depends on how many frames per second they want. So a lot of these high frequency IToF applications, they use an imager, and they're actually taking like a lidar video, and they can adjust the frame rate. So that's one application. That again, it still depends on the laser heating, right? In these applications, they're typically using a VCSEL. Maybe you get 30% electrical to optical. So, the VCSEL gets hot. It dissipates, 2/3 of the power that goes into it. So it's still, I think, limited by the laser.
Okay. Let's see. Okay, next question. With sharp high frequency square waves, it's hard to avoid radiated emissions at high order harmonics. How do you mitigate against this? And then the second part of the question is, do you have design guides to minimize radiated emissions?
John, what do you have to say about that?
It's certainly true, right? The faster the edges you have, the easier it is to couple to the outside world, right? The smaller structures you have. But at the same time, everything we do to minimize inductance is basically shrinking that power loop. And the smaller that power loop is, the less effectively it couples to the outside world. So, all the things, inductance is basically all that energy that, you don't want stored outside the actual structure. So reducing the inductance does reduce the EMI a great deal. There are other paths, and I would say, yes, you have to worry about it, but the techniques are the same techniques you use for EMI and other applications, and the customers are making it work, so it's a solvable problem. And as an aside, and this has nothing to do with GaN actually, is attack your EMI problems up front, right? If you keep your inductances low and think about it up front, you'll save a lot of trouble, in the end. It's hard to put band-aids on at the end, but
I'd also like to just add that with very fast rise and very fast fall times, your frequency spectrum tends to be out in the very high frequency range, which is somewhat easier to filter out as well. So, and a lot of these lidar systems are in metal cans, so the problems have been solved, and it's just solid, straightforward engineering to do it.
Okay. So we had a question about the LVDS part, which actually I can answer. So the question was whether it is in production or will be sampling soon. So that was the device, Alex, that you showed, the EPC 21603. That's targeted to launch by March 16th. But certainly if you need samples in advance of that, we just contact your local EPC sales rep, and we can take care of that for you, because we have devices available now. Okay. Next question is, amplitude can be varied by the voltage, but to vary the pulse width dynamically, you cannot use the resonant architecture. Is that correct?
That is mostly correct. If you have a long enough resonant pulse, you can terminate the pulse early, but that energy still has to go somewhere. Some of it goes into the FET output capacitance. but you don't get very good control. So I would say yes, you're probably correct for almost all cases.
Now,
Go
a
ahead.
couple of things there is that you know, these dual edge control where you turn it on and turn it off, which is, you know, all the IToF ones are dual edge control. But for the very long range DToF one, dual edge control just has the danger of eye safety. What happens if you can't turn it off? And so some people struggle a little bit with that. But in general, you know, as John said, it's determined by the, you know, it is hard to make a longer pulse than a short pulse. And if you make a longer pulse, you cut it off with turning on the or by dissipating it through the FET.
Do the devices have tolerance to humidity?
All our GaN devices are glass passivated, and so they are as immune to humidity as any plastic package part, even more so. They all pass not just humidity testing for automotive, but also are what's rated MSL1, which means they're the most immune to the environment in storage. So you know, basically GaN, because it's built on top of silicon, we can seal it in a glass case from the rest of the world, and the only penetrations are for the solder bumps.
What are the biggest challenges using GaN?
Well, we certainly have a lot of experience. We've been in production now for 11 years, and initially people had a challenge of you know, learning how to use the speed. I always draw the analogy: if you'd grown up your whole life driving a stick shift Volkswagen Beetle, and somebody gave you the keys to a Ferrari and told you to drive it as fast as possible to get home, you'd probably crash along the way. And I think that's also somewhat the case with GaN. It is blazing fast, so people have had to learn how to do layouts that have less parasitic inductance. You know, inductance is not your friend when you're going fast, so that was a challenge. We have lots of guidance on layouts and most efficient layouts and things like that. The second biggest challenge, I think, for folks was handling these tiny little parts. Many people's manufacturing lines had to be upgraded. Their PC board design and design tolerances had to be upgraded. Again, we give a lot of guidance both on our website and through our field applications engineers on how to do that. And I think that once people overcame those two obstacles, they found that GaN devices were as simple as any silicon device to use.
Okay. So I am using IToF for inside the passenger compartment and short range exterior sensing for automobiles. Is there a plan to qualify the new laser driver IC to AEC-Q 100?
Yes, we'll have that qualified to AEC-Q 100, you know, certainly within the next year.
Okay. Can you integrate other functions beyond the gate driver?
Yes. As a matter of fact, in direct time of flight applications, we've been building fairly complex multi-channel laser drivers with all sorts of onboard logic and signal processing. Those have all been custom for lidar producers. So we have a pretty good ability to integrate lots of stuff on here.
Do eGaN FETs truly have no QRR and thus no forward and reverse recovery times?
They have no QRR. QRR is the reverse recovery of a silicon MOSFET. It comes from the fact that in the third quadrant or reverse direction, there is a PN diode that's turned on, and that means that there is an injection of minority carriers. And minority carriers basically have to find a home and die in that home in order to stop conducting. And that's that recovery time. So it's based on the lifetime of those carriers. GaN has no minority carrier conduction and has no diode in the reverse direction. So what we're doing in the reverse direction is just turning back on the FET. And the FET the only limitation to the speed of the FET turning on and off is the capacitance. So if, is there no QRR? That is accurate. Is it infinitely fast? It's as fast as you can turn it on and off, fast as you can turn on and off the forward direction.
Okay, so you showed 100-volt GaN FETs with AEC Q of 101, but I may need higher voltage. Do you plan to have 200-volt GaN FETs with AEC qualification?
Yes, we do. We have a couple of devices right now under qualification, the 2207 and the 2215. This should be completed by the end of the year.
Okay, great. Okay. Let me see. I think that is, okay, someone's asking about the 21603 data sheets. Well, they're not finalized yet, but as soon as they are, we can get those out to you. Okay.
And I would like to point out that the 601 is on the shelf at DigiKey if you want to buy it today.
All right. Well, thank you, Alex. Thank you, John. Thank you, everyone, for attending today's webinar. Our next webinar is going to be easy design tips to maximize performance and reliability in your GaN designs, and that is on March 24th. Topics covered will include gate drive, layout, heat sinking, EMI, and other simple techniques to maximize performance and reliability. So if you have not done so already, please visit epc-co.com to register. If we didn't have a chance to answer your questions or you think of more after you hang up today, please feel free to reach out to us at info@epc-co.com and we'll get answers to that. When you leave the webinar today, you will receive a survey on the presentation, and we would appreciate your time to provide that feedback. And you'll also receive an email within 24 to 48 hours with a link to the viewing of today's webinar. So thank you again for joining us today, and we hope to see you again at the next webinar. Have a great rest of your day. Thank you.
Thank you.